All right, this is the 6th FRQ for the 2019 AB exam. So they give you functions f, g, and h, and they say that they're twice differentiable. They tell you that g evaluated at 2 and h evaluated at 2 both equal 4. They give you the tangent line for both of those graphs, and you can see that here's the 2, 4 right there, right? So for each of these, we have an x-coordinate of 2 and a y-coordinate of 4, and so that's basically y minus 4 equals something x minus 2, right? There's that. And so the number in the front of that is 2/3. So for part A, when they said to find h prime of 2, that's just the 2/3. So mathematically speaking, not difficult to do that. You just have to be able to read the information that they gave you. So they gave you a tangent line, that means that they gave you the slope, which means that they gave you the derivative at a point, which is what part A is asking for. Part B says now you have a function a of x that is 3x cubed times h of x, and they want you to find an expression for the derivative of a and then a prime evaluated at 2. So for part B, go ahead and write the function. We have the product rule, so I've got the first times the derivative of the second plus the second times the derivative of the first. And then we're evaluating that at 2, so I just need to plug 2 in. So 3 times 2 to the third, h prime of 2, plus h of 2, 9 times 2 squared. So 3 times 8 is 24. 24 times h prime of 2 we know is 2/3. And then that's plus h of 2 we know is 4. 9 times 4 is 36. So over here I've got 24 times 2 is 48. 48 divided by 3 is 16, plus 144 equals 160. However, you should be able to leave it here and call it good. You don't need to bring it all the way to the end like I did. All right, part C. So this one is really an interesting question because of them throwing at you that you're doing L'Hopital's rule. So here we're going to say h of x equals x squared minus 4 over 1 minus f of x to the third power. So since they said it can be evaluated using L'Hopital's, that means that at least when I try to take the limit at first, I'm going to get 0 over 0 or infinity over infinity. So I knew that as a first step, so I'm just going to go ahead and do that. So I'm going to say the limit as x approaches 2, x squared minus 4, just writing it all out. So when I do L'Hopital's, then I have to do the limit of the top. So 2 squared minus 4 is 0. That totally makes sense. Okay, and so then over here what I did is I said, okay, let me just take this part and actually solve it out. So 1 equals f of 2 cubed. I can go ahead and cube root each side. I still get 1. 1 equals f of 2. So that part, although kind of funky to set up, was actually not too difficult. Like that part was okay. It's the part after this that starts to get weird because in my head I was like, oh, I'm just going to use L'Hopital's again. And when you try, the top does not equal 0, so it's not L'Hopital's for a second time. So I'm going to go ahead and write use L'Hopital's. And the reason I know I can do that is a result of this 0 and 0 here. That tells me to use L'Hopital's. So now I've got limit as x approaches 2. And then for the top, I have 2x. For the bottom, 0. So I've got negative, I'll drop the 3 to the front, negative 3 f of x squared multiplied by f prime of x. And so I went ahead and did the same thing. I said with L'Hopital's, I know that I need to split the top and the bottom apart, and so I did that. So the top would be limit as x approaches 2 of 2x, and then I went, uh-oh, that's 4. And so this is where I had to be a little bit more careful and think a little bit differently. So I went ahead and I was like, okay, well, at least let me start to deal with the bottom part so I at least know what I'm looking at. So I said, okay, the limit as x approaches 2, -3 f of x squared times f prime of x, that has to equal a number somehow, because they tell us to find the limit of h of x. And if you look back to the original problem, in the original problem they tell you that h is twice differentiable, and if h is twice differentiable, that means that h has to be continuous. So this is something in the problem that's very subtle. They gave you that things in the beginning were continuous, they didn't tell you that. So you really have to understand the definition of continuity to kind of make sense of this next part. So before I do too much more with that, I'm going to say that h of x is twice differentiable and therefore is continuous. So let's just remember, now you don't have to put this on the problem. As soon as you say it's continuous, a mathematician is going to go, okay, I know where you're going from there. However, a beginning calculus student is going to maybe need some extra hints. So just to remind you what continuity means, it means that h of 2 exists, and we already know that, right? We already know that h of 2 equals 4. It also means that the limit as x approaches 2 of h of x exists. So that means that the left-hand limit and the right-hand limit are the same. Okay, good, we know that. And then the third thing is it means that h of 2 equals the limit as x approaches 2 of h of x. That's what the definition of continuity tells you. So that means that if h of 2 equals 4, and this is continuous, that the limit has to equal 4 as well. And that's something in the problem that is very subtle. That is, I think, would be something very easy to miss. So if we go back to this problem, now I know that since I'm finding the limit as x approaches 2 of h of x, it has to equal 4. So that means that if the top of the fraction equals 4, the bottom of the fraction has to equal 1, and that's the key to being able to do this problem. All right, so what I'm going to do now is take this. I've got -3 multiplied by f of 2 squared times f prime of 2, and I know now that has to equal 1 because the limit overall has to equal 4. So f of 2 we know is just 1, so that's -3, 1 squared is 1. Take that -3 divided over, and f prime of 2 is -1/3. So that one was kind of tricky. Okay, part D. So part D wants you to prove that k of x is continuous at x equals 2. So we're going to take these 3 steps. We're going to go through them again. Okay, so they tell us in the problem that g of x is less than or equal to k of x, which is less than or equal to h of x, right? That's given in the problem, okay? So to prove something's continuous, my first step is to prove that k of 2 exists. And that's actually relatively easy in this problem because we're going to say at k equals 2, we have g of 2 is less than or equal to k of 2 is less than or equal to h of 2. We know that g of 2 is 4. We know that h of 2 is 4. So if k evaluated at 2 is between 4 and 4, then guess what that equals? K of 2 equals 4. And if k evaluated at 2 equals 4, that means that it has to exist. There's a value for it. Okay, so part 1 of the definition of continuity is satisfied. Part 2 is the one that is a little bit more tricky. So here we're going to again say, we already said in part C that h of x was twice differentiable, therefore it was continuous, but we're going to say that with g of x as well. So g of x and h of x are twice differentiable and continuous, and therefore they are continuous. On 1, 3, which is the interval they gave us for the problem. Okay, so now what we have to prove for the second part is we have to show that the limit as x approaches 2 of k of x exists. All right, so if I want to know the limit as x approaches 2 of k of x, and I know that that is in between g of x and h of x, then I'm going to put it in between the limits of those. Limit as x approaches to g of x, limit as x approaches to h of x. So this is kind of using that same idea from part C. We're saying that if we know that those other two were continuous, then not only were they able to be evaluated at 2, but their limit at 2 had to have been the exact same value for them to have that definition of continuity. So here we can say, all right, so the limits are also 4. And so the limit as x approaches 2 of k of x has to equal 4. And what we were able to do here in calculus, this has a title, and it's called the Squeeze Theorem. And I'm pretty sure we did it in the first unit. So this is by the Squeeze Theorem. Okay. So we've got the second part of the definition of continuity. And then the third part, follows after that we have k of 2 equals the limit as x approaches 2 of k of x, which is to say that 4 equals 4. And so that's a check mark. So we've got the whole definition of continuity there. And so now we can say, to summarize, is k continuous at x equals 2? Yes, k is continuous at x equals 2. And then all this work that I did here is the justification of the reasoning using calculus because I'm using that definition of continuity.